So, first homework, chapter 19. That will be due on Friday the 30th. On Pearson, the chapter 20 homework is going to be due on Wednesday the 4th. And we have our first lab today. And hopefully it'll be reasonably quick. So, because I didn't do a very good job explaining flux and Gauss's law last time, I'm going to try to do that again, but this time better. So electric flux is sort of a way to measure the amount of electric field passing through a surface. And strictly speaking, it's sort of a measure of electric field perpendicular to that surface. So the definition of electric flux is electric field times area times the cosine of the angle between them. It's like an integral of the dot product of the normal of the surface and the electric field over the surface. You're adding it up over the whole area. And the unit is Newton. You know, it's Newton, Coulomb, meters squared. Newton meters squared per Coulomb. Newtons per Coulomb is electric field. Meters squared is the area. So basically, you're just adding up how much electric field is going through the surface, accounting for basically the angle of the surface. So, if the electric field is parallel to the surface, it's not really going through it. Lots of things have flux. You can think about light having a flux. So here I'm blocking a decent flux of light. And as I rotate this, I block less and less. That sort of expresses the angle thing. But the thing that makes this useful is that it turns out each little bit of charge puts out a certain amount of total flux. That if you enclose it, that's how much flux would exit a sealed volume. So Gauss's law is that the electric flux through a closed surface, so the amount of flux that comes out of a sealed volume, you have some closed surface, the amount of flux that comes out of it is proportional to the charge that's inside it. Because each little bit of charge puts out a certain amount of flux. So Gauss's law says that total flux equals charge over epsilon naught, where epsilon naught is 1 over 4 pi k, or 8.85 times 10 to the minus 12 Coulomb squared per Newton meter squared. And epsilon naught, it's called the permeativity of free space, or the free permeativity of space, something like that. And that is, it's a property of the universe. So if you have some arbitrary surface, it has a certain amount of electric, you can work out the total electric flux that's coming out through that surface. That tells you how much charge is enclosed within the surface. So in systems with simple configurations or a lot of symmetry, you can use Gauss's law to work out what the electric field should be. You can actually use Gauss's law, start at Gauss's law, and basically derive the electric field of a point charge, the electric field of a line of charge, things like that. The electric field of a parallel plate capacitor. And knowing that the electric field inside You can also use it to figure out things like how much charge is going to be in charge distributions and such for conductors, because the the electric field inside a conductor is always zero. So that's what I wanted to sort of go over. We did a couple example problems of that last time. So now that we've talked about electric fields and electric flux and stuff, let's talk and why. And like there's a more advanced version of Gauss's law with multivariable calculus that you can use to basically go from an electric field distribution over space to a charge distribution and vice versa. But we're not going to do that because that's just ugly integrals all the way down. But yeah, so there's a way that if you know the electric field everywhere, you can figure out how charge is distributed, but with like divergence and such. So electric field is related to force. Electric potential is related to potential energy. So you've probably encountered electric potential. It is more commonly referred to by the name of its unit, the volt or voltage. Voltage is a measure of electric potential. So we're going to talk about how electric potential energy and the electric potential are connected. We'll discuss energy conservation, the electric potential of point charges, equipotential surfaces and the electric field, capacitors and dielectrics, and electrical energy storage in this chapter. So the electric force is a conservative force. It has all the properties of a conservative force, so it has a potential energy associated. It takes work to move an electric charge parallel to an electric field opposing that field. So the work against an electric field is minus the charge you're moving times the electric field times the distance you're moving it over. This is assuming you're moving this opposite the direction of the electric field. So here we have some electric field E, and we have some charge Q, and we're moving it some distance D against the electric field. So it takes some work to move a charge parallel to the electric field opposing the field. And as usual, the change in potential energy is the negative of the work. So change in potential energy is minus work, which is Q naught, times the electric field times the distance. So we have another thing where we have some Q naught. We have our, change in potential energy is equal to Q naught times electric field times distance. This is similar to moving a charge in a gravitational field, where we have mg times distance. Here we have Q naught E times distance. So just as it was useful to define an electric field in reference to some test charge, it's useful to define an electric potential in reference to some test charge. So basically, we just divide both sides by Q naught, and we get delta V is change in electric potential over Q naught, or minus work over Q naught. The unit is a joule per coulomb, because it's energy over charge, so it's joule per coulomb, and that unit is the volt. There's also a unit of energy called an electron volt. An electron volt is 1 quantum of charge times 1 volt, and it's a useful unit of energy for describing energy at the scale of particles. So it gets used a lot in particle physics, or talking about particles, or talking about molecular stuff, things like that. So I think, for example, off the top of my head, the amount of energy you need to ionize hydrogen, for example, is 13.6 electron volts. So you need 13.6 volts affecting an electron. And an electron volt, so 1 electron volt, it is E times a volt. So it's 1.60 times 10 to the minus 19. And the electric field is related to the rate of change of the electric potential. So electric field is the derivative of potential over distance. It's minus the derivative of electric field over potential. So it's minus delta V over delta S if it's constant, or it's minus dV ds. I'm rusty at, strictly speaking, how you do it properly in multivariable calculus, but it's basically a derivative. And it might be the divergence. The other thing, the other thing is that the electric potential voltage is a scalar. It is not a vector. It does not have a direction. So that is really helpful, because then you don't have to worry about adding vectors properly. You can just add numbers. Much like energy makes things easier than working with forces because it's not a vector, electric potential makes things easier than working with electric fields because it's not a vector. So if you have something like this, capacitor, parallel plate capacitor, it has a constant electric field between the plates. That corresponds to a constant decrease in electric potential. It has a linear change in electric potential. So one side has a higher electric potential, the other side has a lower electric potential. So if we want to find the change in electric potential energy when a charge moves from point A to point B, where we have a potential difference, delta V, of plus 12 volts. And it's a charge of 3.63 microcoulombs. So remember, electric potential is change in potential energy over charge, which means change in potential energy is change in electric potential over delta V times charge is delta U. So delta U is going to be charge times delta V. So that's 3.65 microcoulombs, so 3.65 times 10 to the minus 6 coulombs. times 12 volts, which is 4.38 times 10 to the minus 5 joules. Here, let's talk about what the electric potential passed through when the electric potential energy of a charge of 1.5 microcoulombs decreases by 2.7 times 10 to the minus 5 joules. So here we're looking for electric potential. We know of delta U and Q. So this is delta U, that's Q. Delta V, change in electric potential, is delta U over Q. So that's 2.7 times 10 to the minus 5 joules over 1.5 times 10 to the minus 6 coulombs, which is a change in electric potential of 18 volts. Now, here we have a capacitor hooked up to a battery, something that creates a difference in electric potential. We have a 12-volt battery. So a uniform electric field is created by applying the plates of a capacitor to a 12-volt battery. If the plates are separated by a distance of 0.63 centimeters, what is the magnitude of the electric field? And if a charge of 0.46 microcoulombs moves from the positive plate to the negative plate, what is the change in electric potential energy? The positive plate will have a high voltage, the negative plate will have a low voltage. So this has two distinct parts. First, the electric field is minus delta V over delta S. So that's minus 12 volts, because we're going from positive to negative, from plus 12 volts to minus 12 volts, over 0.0063 meters, that's 0.63 centimeters. That will give us an electric field of 1900 volts per meter. We're looking for the magnitude, so you can just take the absolute value of whatever you get, but that's the general idea. We have a change of 12 volts over a distance of 0.0063 meters. It's going to go from the high voltage to the low voltage. The electric field points downhill from high voltage to low voltage. That's why there's the minus sign. And the change in potential energy is charge times change in voltage. So that'll be 4.6 microcoulombs. So 4.6 times 10 to the minus 6 coulombs times minus 12 volts, which is minus 5.5 times 10 to the minus 5 joules. That change is going to be negative because it's going from high voltage to low voltage. So it is losing potential energy. Again, it's like rolling downhill. And here's another example. We want to find the electric field and the potential difference. So the electric potential at point B in a parallel plate capacitor, shown in this sketch, is less than the electric potential at point A by 4.63 volts. So from here to here, delta V equals 4.63 volts. And the separation between points A and B is 0.67 centimeters, and the separation between the plates is 2.01 centimeters. So find the electric field within the capacitor and find the potential difference between the plates. So for this, to find the electric field between the capacitor, we'll use that the electric field is minus delta V over delta S. And our delta V for this first part is 4.63 volts. And our delta S is 0.670 centimeters. Electric field, delta V over minus delta V over delta S. So it's minus 4.63 volts over 0.00670 meters. So the electric field is 691 volts per meter from the positive plate to the negative plate. Then to find the potential difference between the two plates, well, now we know the electric field, so we can repeat using this equation, but instead with a new delta S, or delta S1 maybe, this is our new delta S, and we can find the new delta V. So delta V is minus E times D. Delta V is going to be minus 691 volts per meter times 0.020201 meters, which is a voltage of 14.5 volts. So basically, electric field is the derivative of the voltage, and it has a direction. You know, it's a Any questions? So, in a certain region of space, the electric potential is known to be constant. So we have some region of space, and we know the electric potential throughout this region is constant. So if the electric field is constant, if the electric potential is constant, if the voltage is constant, is the electric field in the region positive, negative, or zero? So what do you guys think? Positive, negative, or zero? So remember, the electric field is basically the derivative of the electric potential. So if the electric potential is constant, is the electric field positive, negative, or zero? Yep. Electric field is minus delta V delta S. Delta V is zero because electric potential is constant. So electric field is zero. That's what happens inside a conductor, for example. In a conductor, you have no electric field. The potential throughout a conductor is always constant. Now, energy is conserved. So in general, for any mass moving from point A to point B in a conservative force, kinetic energy plus potential energy equal initial equals kinetic at point A equals kinetic energy plus potential energy at point B. If you have an electric force, potential energy is just charge times the voltage. So you get, kinetic energy at point B, 1/2 mass times velocity v squared is going to be 1/2 mass times velocity a squared plus charge times change in voltage. VA minus V. So if you want to figure out if you release, if some particle moves through an electric field so that there's a change in electric potential, you can work out its change in kinetic energy. So you can work out how much energy you're going to get from this. So since the force on a negative charge is opposite to the field direction, positive charges will accelerate in the direction of decreasing electric potential. They go down towards lower voltages. Negative charges accelerate in the direction of increasing electric potential. They go up towards higher voltages. Because unfortunately, the charges that actually move around in circuits, for example, are negative. This means the actual electrons flowing through a circuit tend to be moving towards the higher voltage from the lower voltage. Yeah. And in both cases, the charge moves to a region of lower potential energy. And if you had a positively charged particle in a voltage difference, if you have a voltage difference and you release a positively charged particle and a negatively charged particle, positively charged particle will go one way, the negatively charged particle will go the other way. So if you have a particle with mass m of 1.5 times 10 to the minus 5 kilograms and charge q of 5 times 10 to the minus 5 coulombs, and it's released from rest at a point A, and it moves to a point B where the electric potential is 60 volts lower than point A, how fast will it be traveling at point B? So it goes from point A to point B, and it goes from an electric potential of maybe from 0 to minus 60 is the way to think about it. But it goes down, delta V, the change in potential, is negative 60. No, it's positive 60, sorry. Let me just go back to this. Yeah, it's V, that is VA minus VB. So I will write that out with VA minus VB. One problem with this particular equation is that there's an important difference between capital and lowercase. Let me rewrite this. So, we have 1/2 mass times velocity v squared equals 1/2 mass times velocity a squared plus charge times voltage A minus voltage B. That's clear. So here we have a positive charge going down in potential. So this term, voltage A minus voltage B, will be positive because point A has a higher voltage than point B. So to start with, change in potential energy is charge times delta V. Change in kinetic energy is minus change in potential energy. So 1/2 mass times velocity final squared minus 1/2 mass times velocity initial squared is going to equal change. Minus change in potential energy, or minus Q delta V. In this case, delta V is minus 60 volts. Our initial velocity is 0. Our final velocity is what we're interested in. So 1/2 mass times velocity squared will end up equaling minus Q delta V. The velocity squared is minus 2Q delta V over mass, or the square root of minus 2Q delta V over mass. So if we plug in our numbers, 2Q is 5 times 10 to the minus 5 coulombs. Delta V is negative 60 volts, because we dropped by 60 volts. And 1.5 times 10 to the minus 5 kilograms is the mass. The minus signs cancel. The 10 to the minus 5s cancel. And we get a velocity of 20 meters per second. If you wanted to use this equation a little more directly, it's 1/2 mass VV squared equals 1/2 mass 0 squared plus Q times 60 volts. So VV squared is going to be 2Q times 60 volts over mass. So V equals square root of 2 times 5 times 10 to the minus 5 coulombs times 60 volts over 1.5 times 10 to the minus 5 kilograms, and then that gives you 20 meters. So here we have a parallel plate capacitor again with a voltage difference of 12 volts, a charge of 4.6 times 10 to the minus 6 coulomb is released from the positive side of a capacitor with a potential difference of 12 volts. When it reaches the other side, it's traveling at 3.5 meters per second. What is the mass of the charge and its final kinetic energy? It's actually easier to work the other way around. Final kinetic energy is easier to calculate than mass. So we'll find final kinetic energy and then work out mass from the velocity. Parallel plate capacitor, accelerating something like this, that's used in lots of things, like electron guns in a CRT TV, for example. So, how would you go about doing this? Well, let's start by finding the final kinetic energy. We know a charge, we know a voltage. That tells us a change in potential energy. That's going to be minus the change in kinetic energy. So, change in potential energy is charge times change in voltage. Kinetic energy is minus change in potential. The change in kinetic energy is minus change in potential energy. So final kinetic energy minus initial kinetic energy is minus Q delta V. Our initial kinetic energy is 0. So our final kinetic energy ends up being minus 4.6 times 10 to the minus 6 coulombs times minus 12 volts. Because it's going from the positive side to the negative side. So delta V is minus 12 volts. So our change in kinetic energy is 5.52 times 10 to the minus 5. That's our final kinetic energy. Then we want to find the mass of the charge. Well, we know its kinetic energy. We know how fast it's traveling. Kinetic energy is 1/2 mass times velocity squared. So mass is 2 times kinetic energy over velocity squared. So mass equals 2 times 5.52 times 10 to the minus 5 joules divided by 3.5 meters per second quantity squared, which is 9.0 times 10 to the minus 6 kilograms. Any questions about that? So just remember that voltage corresponds to potential energy. So an electron, which has a charge of minus 1.6 times 10 to the minus 19 coulombs, accelerates from rest through a potential difference of V. A proton with a charge of plus 1.6 times 10 to the minus 19 coulombs accelerates from rest through a potential difference of minus V. So we both have an electron and a proton. One goes through a potential difference of plus V. The other one goes through a potential difference of minus V. Is the final speed of the electron greater than, less than, or the same as the final speed of the proton? And which do you think is the best explanation of this? Is it the electron has greater speed because it has the same kinetic energy as the proton but less mass? 2, the electron has less speed because it has less mass than the proton? Or 3, both particles have the same speed because they accelerate through a potential difference of the same magnitude? What do you think is the case here? 1, 2, or 3? Yes, 1 is correct. They both have the same kinetic energy because they went through the same potential difference and they have the same charge, magnitude-wise. The signs are opposite, but they actually end up with the same kinetic energy. But the electron is going to be going faster because it's light. So the same energy will make it go faster than the proton. It's going to be going quite a bit faster, actually. Maybe not a huge amount, but it's a lot lighter than a proton. So we talked about electric potential and how it's related to electric field. Well, let's work out what the electric potential of a point charge is. Well, the potential energy difference between points A and B related to a point charge is going to be K Q naught Q over radius A minus K Q naught Q over radius B. You can take the force and you basically integrate over the force to get the potential energy, and you'll get this formula. Which means for a point charge, we get a useful electric potential for a point charge by saying that the electric potential of a point charge is KQ over R. And our general assumption is the one assumption we use for this is that we assume that the electric potential at a distance of infinity is 0. So the general way that we approach electric potential for something like a point charge is that far, far away is 0 electric potential. And then you get either more and more or less and less as you get closer, bigger and bigger magnitude as you get closer to the point charge. So this is the electric potential of a positive charge. This is the electric potential of a negative charge. K is 8.99 10 to the minus. Let me just. I think it's 9, but I don't want to get it wrong. 10 to the 9. Not modified. Coulomb squared over meters. And so electric potential, KQ over R. One of the nice things about electric potential, it's a scalar. We no longer have to worry about direction. So if we want to combine the electric potential from multiple charges, you just have to add them. You don't have to worry about what direction they're pointing. So the electric potential of a group of point charges will just sum. The algebraic sum of the potentials of each charge. So this is a plot of the electric potential of these two charges. Nope, this is in fact an excellent stopping point. This is when we're supposed to stop. So that is where we're going to stop for today. It is 3:15. That's when we're supposed to stop. So we will stop there. I will stop sharing.